So my talk will be today about miniaturized multi-aperture microscopes, which we developed here at Fraunhofer during the last years, I would already say. So maybe just, yeah. So our institute is mainly dedicated to all kinds of optical elements and optical systems, and we have a department where we are dedicated to the lithographic realization of micro-optical elements. Here is just exemplarily shown Fresnel lenses, customized Fresnel lenses, beam splitters with anti-reflective coating for ultra-broadband spectrum usage, polymer on glass replication, and also the lithography on non-standard substrates like these curved mirrors. And then we built from that off micro-optical systems or miniaturized optical systems, for instance, for very popular for illumination, like here, compact array projection, tailored light diffusers to tailor the distribution to certain field of views, miniaturized and ultra-compact imaging systems, very flat. Here amongst them, the flat microscope I will talk about, and then also and multispectral imaging acquisition, where we have different filters here inside a very compact system to get a broad spectral imaging and make such data cubes. So the first question is, can we scale down the optical instrumentation to its final object size? So typically when we have samples in life science, microfluidics, or point of care diagnostic, they have typically a size of, let's say, 1 square inch. But contrary, the instrument for analysis has the size of more a magnitude larger. And the idea is how to compactify this optical beam path here to make it smaller. And of course, you know, the applications where they are needed. For instance, the portable microscopy, also cell monitoring is one target application here. Also in workbenches with where you are working in sterile, anaerobe, or biohazard environments, then you would be lucky to have not such an open system like here, but have a small and compact device, or also digital pathology, where you want to have at least large area scans to be detected. So, and the requirements from these applications are typically resolution. You need at least 1 micron to detect certain features of cells. Yeah, like for instance, Golgi compartments and so on. And you want, or it's needed to have at least 1 bright field, and it's highly appreciated to have 1 or 2 fluorescence channels to detect. And you want to have a large area in the range of a microscopy slide here, this 1 inch times 3 inch. So what can you do? How to reduce the size of an image system? Luckily or helpfully, while increasing the field of view. So the standard microscope objective has a certain magnification, numerical aperture, defining the resolution and also the field of view. One direction is, of course, when you reduce the magnification, then you get a larger field of view, but then you lose also resolution. The other way is the way from lithography. You increase the field of view with a high resolution, then you have to increase these optics. And you can imagine from the lithography systems that you have very large and bulky imaging optics that have a very high resolution to image in high quality a certain field of view. And there's the multi-aperture imaging approach, where you have parallel optical systems which are scalable to the field of view you need, and having here each individual a very small field of view, you have even a simplified optics. So, and this is the way how we shrink our micro optics or microscope imaging systems. The one simplest version is to have a system with unity magnification, which means that in the imaging path, you have a certain simple lens, for instance, and you see a field of view in the object. And for the imaging, has more or less the same optical distance. You can image this to a certain sensor, and this have an optical tiling where you have the field of view, for instance, here from certain areas that are tiled and stitched again by optics on the sensor, on the image sensor. And this helps us to scale it to image sensors. Even a full frame sensor of 24 times 36 millimeters could be used here with an homogeneous micro lens array to use it as rather a close up image device, not really a microscope. Because we have just the magnification of one. Yeah, it's also you can combine this also with top side illumination that you can even see here the fingerprint. Although there is no transmittive light, it's an up or EP mode microscope or close-up imaging device. So, but when you want to magnify, then it changes a little. So the optical stitching now is not possible directly anymore, but you need a certain scan because if you have just this small image and you image it to a larger area, then the next one is not directly adjacent to this anymore. You have not the space here in image in the image plane, and so you have to scan. And there are two different ways to scan, but what you gain here is with this larger magnification, you can increase also your numerical aperture here, and you have the chance to resolve, for instance, micro-optical cells and biological images like cells and so on. And this was realized with this compact system here. So we have here in this system path everything we need for an imaging and a scaling with a certain resolution. We have here an object with a certain cover class topping. We have a working distance of 450 microns. Have a tool with micro lenses here on the bottom is a very shallow one, and here is even an achromatic micro lens on top. And using a fluorescence filter here for also discriminating certain functionalities. Then here is above the image sensor, even with its cover class. So this track length here is approximately 10 millimeters, which is very compact. And this is realized by making these micro lenses with lithography approaches, using also black metal apertures here that we can suppress crosstalk between neighboring channels, and we get a very flat, nearly a plate, which we can then place in front of an image sensor for large image sensors like this full frame with 12 megapixels or smaller one here. And then you have, if due to the increase, it's not a snapshot anymore, but you can use it with a scan. So if you have a magnification of M, magnification factor, then it needs at least M square of scan steps to cover completely the full object. And you have two possibilities. You can make a 1D scan, rather by displacing here the channels slightly with a tilt angle, so that you can cover by scanning linearly each spot of the object. Or you can have it, and this is typically done for smaller systems, using a 2D scan. Then you have to, of course, move in 2 dimensions to cover here. And both options have been implemented here. For the large area of a 12 megapixel full frame sensor, it's rather easier to move the object. Whereas for a small area and a small image sensor, it's also possible to move the optics and the sensor itself, because then it's more lightweight, and this movement could be also made fast. So, and what happens from the data or from the recorded images? If you would have a static image, what you see from multiple channels here, they are arranged in hexagonal arrangement. You have all these channels, and each are taking a certain part of the image of the full frame. And then when moving the sensor or moving the image, then we can lead this to a stitching across the scan dimension. And afterwards, then from software, we blend these images in order to get a flat field correction and a color correction and so on. We consider the filter function for fluorescence filter and so on. And then we get final result, a stitched image, which has a shading correction and so on. This is then, of course, not anymore a snapshot, but with scan, it's quite easy to get a full area like these 12 megapixels in a very, very short time. To have now built up the complete system, of course, we need also the illumination here. There are 3 illumination sources for transmitted light configuration for this microscope, 2 fluorescence wavelength and 1 white for bright view. And we place here, for instance, these microscope slide into, and then we can, with different pattern illuminations, we can then look at the surface and different channels and gain the images from software stitching. Or for the small system here, it's shown it's very, very compact. It has only 3 cubic centimeters of total image optic size, and it's quite easy to have this as a compact and a portable device, for instance, for point of care diagnostics. So with the left, or maybe just go back, with that sample here, or with this system, we received this information here. So we have an array of optical channels, each giving the information from a certain field of view. And by stitching together, I would see it's quite dark. I hope you can see that there is again this scan line here where you scan multiple in one linear direction, and then from that one could stitch finally and overlap the information from a quite large field of view. So from here, a total field of view much larger than 10 by 10 square millimeters. We have the information of a bright view field of these cells, of these HeLa cells, and also a fluorescence signal of these HeLa cells, and they are overlapped and correlated to each other in a very compact, robust device. So my summary and outlook here. So we demonstrated that we can build multi-aperture microscope objective, and these are really miniaturized imaging devices. The typical size here for the demonstrated system has approximately 10x magnification and a numerical aperture of 0.3. So it delivers a resolution better than 1 micron. It's usable with bright field and bright light illumination and also fluorescence modes. The illumination optics is optimized by Fleiss eye condensers and similar to a normal microscope, standard microscope. I showed you that there are 1, 2, or 2D scanning approaches available to cover the complete target size. And we apply, of course, adapted stitching algorithms. And the advantage we have here is, of course, the optics is very compact. We are not much larger than this image sensor itself, maybe 1 centimeter in track width. And another advantage from fabrication is that all the optics is in the end passively aligned, because the high resolution lithography approach for one array already delivers the placement accuracy. So this is really are not only for these microscopes, but also imaging devices we could use here. They can be used in compact spaces and could be applied to difficult workplaces. And one outlook, not shown here too much, is a new device where we increased the numerical aperture of a microscope for 8 channels to 0.65, also with white light source and 3 different fluorescence filters here for an image-based cell sorting line, where the prototype is shown here. And another outlook here is the adaptation for the microscopic concept to a microspectrometer array, where we have here a compact array where we have in each channel 3 local spectrometer data available for a complete multispectral or hyperspectral information. And this is then possible to have more than 30 channels at all available for different analysis at different positions, because this is a fiber coupled concept, and each fiber, of course, could be could be pointed to a certain different spot. So the typical epic questions here for the final summarization, what can we do for you, is of course the design and realization for micro-optical beam shapers and miniaturized optical systems at all, and build from that of prototypes of optimized microscopic devices for your specific application. And of course, we also provide design studies, the prototyping, and also the small series fabrication. So what can you do for us is, show us your use case, your specific use case, or your application scenarios, and we can find together a solution for compactification, or and make it miniaturization. We are partners in research projects, and we are looking for compact sensor self-developing kits that we can build prototypes, because often it's like this, that the microelectronics is then larger than the very optimized micro-optics. Yeah, so the microelectronics is typically larger than in the end. So if it's possible to have it more compact, then it's would be helpful for us. And that's the end of my talk.